Okay, so today we're going to be finishing up chapter 36. So this is the last of the new material that we're going to be learning before the final on Tuesday. Now, just a couple things about the final first. So as I mentioned before, it will be cumulative, but don't worry too much about the fact that it's cumulative. It's going to focus on chapter 35 and 36 since we haven't been tested on that before. Now, it'll probably be the pretty much like the same setup as the midterms. I'm not sure if I'm going to include multiple choice yet or not. But if I do, it'll be like 5 multiple choice like before. And there'll be 4 or 5, depending on how long they are. 4 or 5 short answer problems, since we have 2 hours now to do the exam instead of like an hour and 20 minutes or whatever. So 4 or 5 short answer, depending on how long, how many parts they have. I would expect like half of them. So if we have 4 questions, 4 short answer questions, expect like 1 from chapter 35 and 1 from chapter 36. And the other 2 might be maybe something about standing waves or something like that. Or maybe even 3 questions from chapter 35 and 36. But like at least 50% of the exam will be from chapter 35 and 36. And then the other cumulative subjects will be like the big picture stuff from our previous chapters. So there won't be any chapter, I won't include anything from chapter 16. So no sound, no pipes, no overtones, no Doppler shift. So I won't include anything from chapter 16 because I think chapter 16 was a little bit of sort of like a standalone chapter as far as the hearing and sound went. The type of problem that would come up is, like I said, a standing wave problem, a periodic motion problem. Those were kind of the themes of this course, or harmonic motion, periodic motion, standing waves. So something more along that vein sort of would be the cumulative part. I will go into a little bit more detail. So I'm hoping to get a final review up, if not Friday, hopefully by Saturday. So I'll go into a little bit more detail. I'll also probably have the exam made up by then. So a little bit more detail about the cumulative aspect of it. But again, the main big picture things from this class are waves, standing waves, harmonic motion. And I also won't put, one of the short answer questions will not be a purely geometric optics problem. So like we had in the last exam, we have like a lens and you have the focal length of the lens and find the position of the object and the image, whatever. That type of question will not be one of the short answer questions. So it'll be something more to do with waves and standing waves. Okay. So that being said, so we can move on now to the last part of our chapter 36 material. So in our previous lecture, we saw that when we have light going through some slits, we get this central maximum here that's obviously very bright. And you can see from the picture that as we go out along the pattern, the intensity of the light falls off. So how do we calculate the intensity of these successive, maxima here and, the minima too? How do we know where they are based on the intensity? Well, we know that it'll depend on the phase difference, right? Because where the waves cancel out and where they interfere constructively will depend on the phase difference of your waves as they hit that point on the screen. So the phase difference is going to be equal to 2 pi over lambda times the path length difference. And I think you probably saw this in chapter 35 as well. So this is how you can calculate where the intensity is a maximum, where it's a minimum, and figure out the intensity of these bright spots. Now you can use Huygens principle like we mentioned last time. You can use Huygens principle, you can use this phase difference, and then you can calculate the amplitude of the electric field. You can use a phasor diagram for it. We're not going to really cover phasor diagrams because I'm not planning on testing you on them. But if you are curious, you can look in the book. They do go through like the proof with phasor diagrams. Again, you can, like I said, you can use Huygens principle also to go through it. But we're just going to take the intensity formula basically as a given. So the intensity formula for the bands on this screen is given by this formula. Now I know that's very ugly. So let's just go over it very carefully. Now again, you can derive this using this formula phasors and Huygens principle. But what we get to is this answer. So be really careful because you have a sine of a sine. So here, what we have is I is obviously the intensity at some point. So that will be like the intensity here or here or here, anywhere. So this is your intensity at some point. I naught is the peak intensity at the maximum here. So that would be over here. This is your I naught in here. Then you have sine of pi times a, where a is the slit width, times sine of theta, where theta is just like what we did on Tuesday, where it's the angle from the middle of your slit to whatever point you're looking at, you're measuring the intensity at, divided by pi times a, the slit width again, times sine theta, same thing, divided by the wavelength of the light. And then you square all of that, and that gives you the intensity. Now we can rewrite this in a slightly simpler form, but it only simplifies what the equation looks like. You still have to plug in all the same variables there. So we can rewrite this. As you can see, we have this term pop up both in the numerator and the denominator. Is pi a sine theta over lambda pops up right here, and then it also pops up in the denominator. So what we can do is just redefine that and call it beta. And this is essentially the path length difference between, so if we have our, let's say we have a slit here like this, and we have a light ray going this way, coming out like this. Beta is basically the path, the phase difference between your top ray and your bottom ray here, if this is the top of the slit and this is the bottom of the slit. And you can do exactly, the same thing that we did on Tuesday. Make a little triangle here. This is the path length difference. This is this is the length of the slit. Call this theta. And then you'll have here, that this path length difference is sine theta times a. So we see that right here. We have our a times sine theta. Draw that here. So this is the path length difference that we had from Tuesday. And then right here we have our 2 pi over lambda, which we said before was our phase difference. So you can see that here we have exactly the same setup of the formula. So basically beta is just the phase difference between a ray coming from the top of your slit and the ray coming from the bottom of your slit. And again, you can use Huygens principle to show that this is how you calculate the intensity, but we're just going to take it as a given since Huygens principle is overly time consuming. So we can rewrite our intensity in terms of this beta here. Now, one thing that is really easy to make a mistake on, so you have two signs, obviously. So you have a sine of theta. Now, theta you can take either in radians or degrees. Just be careful whatever the problem gives you. Usually it will give you theta in terms of degrees. It will say, like 1 degree, 2 degree. Remember, it's always going to be small. So it will give you sine of, tell you theta. And it's fine if you use degrees for that. But this beta here, so when we have beta is equal to 2 pi over lambda times a sine theta, this is radians. So this here must be in radians. So when you define beta this way, it is assuming that beta is in radians. So make sure then that when you're doing a problem, you calculate beta here. When you go to plug it in here and do your sine beta over 2, make sure then that you do it in radians, not degree. So this one over here is fine to do in degree if the problem gives you degrees. Beta here you must do in radians. This is defined as a radian. Okay, so now just let's go on and look at this a little bit more closely. So we can see here we have a diagram of the intensity, and you can see that once we get to like m equals 3, the intensity is like, so little of its original intensity. It's basically nothing. You have 0.008 of the original intensity. So that's why usually we only deal with things up to like m is equal to 3, because once you go beyond m is equal to 3, your intensity is essentially 0. So it falls off very rapidly. Now let's think about where these dark fringes are. So I'm going to rewrite my intensity formula. So we had sine of beta over 2, and then it was all squared. Now we can see here that we're going to get a 0. The intensity is going to be 0 if sine of beta over 2 is 0, right? So we'll have I is equal to 0 if sine of beta over 2 is equal to 0. And now, when is sine of beta over 2 equal to 0? Well, we can look at our sine plot, right? And we see that it's at 0, pi, 2 pi, 3 pi, etc. So sine of beta over 2 is going to be equal to 0 when beta over 2 is equal to an integer multiple of pi, right? We can just see that right here. It's 0 whenever we have an integer multiple of pi. And now if I just want to solve for beta there, I'll just get that beta is equal to 2m pi. So now what this means is that we get a dark spot whenever beta is an even integer multiple of pi, right? Because now I have this 2 here. So I have 2 times any integer is going to be an even number. So any even integer of pi will give me a 0 there. And so now remember we said that beta is equal to 2 pi over lambda a sine theta. So that means that when this is a multiple, an even multiple of pi, we'll get a dark spot, right? So now let me just simplify this formula a little bit. So we'll see our 2's cancel, right? Our 2's cancel here, our pi's cancel. So what we're left with is we have a sine theta is equal to m lambda. And we said that that's where we're going to have a dark spot based on the intensity here, right? So we start with the intensity, found beta, then plugged what we know beta is into here. And we found this formula. Now this was exactly what we had on Tuesday for the dark spots of a single slit. So these match up and it's consistent. So that makes sense. So that's exactly what we found before, and we would expect that to still hold true, obviously. Okay, now let's look at another case. So I'll just write it again so that we have it right here. So we have sine beta over 2, beta over 2. So now what happens if beta is equal to 0? So here we found dark spots, and we're assuming, remember, that m is equal to an integer. So we're not, even though I drew 0 here, we're not including m is equal to 0. Because remember, in this formula too, we started at m is equal to 1. So I'll write that here, when m is equal to plus minus 1, plus minus 2. So we're not including 0. But we know that there's a central bright spot in the middle, right? And that would correspond to where beta is 0. So if beta is 0, and we plug that into this formula, we get 0 over 0, right? So that, if you remember from your calculus class, when you have 0 over 0, that's your indeterminate form. You need to use L'Hopital's rule. So we need to actually use L'Hopital's rule. And we can just take the limit as beta approaches 0 of the intensity, and you will actually find that this formula, as you take the limit as beta approaches 0, it does actually limit out to the maximum intensity I naught when beta is equal to 0, which is what we would expect, right? We expect when beta is 0 for that central maximum to be equal to the maximum intensity. But you have to do L'Hopital's rule to see that. Okay, now let's look at how to find the intensity maximum. So we found that central intensity maximum, we have to use L'Hopital's rule. For the other maxima, if we want to find the other maxima of our formula, so we know where the minima are, but if we want to find any of the other maxima, now if you want to find where this function is a maxima, normally what you would have to do, since we have a beta both in the top and the bottom, what you'd have to do is take the derivative of this function with respect to beta. But if you try doing this, so if you just try doing this, you're going to get something that looks like this. And then when you take the derivative of inside these parentheses, you're going to get cosine beta over 2, and then you're going to have like still more betas on the bottom. So you're going to get a function that has a lot of sine and cosines of beta, and then you're also going to get other betas on the bottom here. You have to do like the whole quotient rule and everything. So this is a transcendental equation because whenever you have basically like a beta inside a sine or cosine function, but then you also have beta outside your sine or cosine functions, and you're trying to solve for beta, you can't do that with any basically like closed form solution. So you can't just solve this like algebraically and say, okay, well, beta is equal to like cosine inverse of something, whatever. So you can't solve equations like this. You have to do it numerically. So if you wanted to find the intensity maximum of this equation, you would need to do it numerically, which obviously we're not going to be doing. So we can use an approximation that will be close enough. So so this is transcendental, and we need numerical methods. So what we can do, like I said, is just use an approximation that's close enough, and we'll say that our approximation is when sine of beta over 2 is equal to plus or minus 1, right? So we'll say when sine of beta over 2 is equal to plus or minus 1, that's close enough to our maximum. And again, we'll see that sine is equal to plus or minus 1. We have pi over 2 here, 3 pi over 2, 5 pi over 2, etc. So sine of beta over 2 is equal to plus or minus 1 when beta over 2 is equal to m plus 1/2 pi, right? That's just pi over 2, 3 pi over 2, 5 pi over 2, where m is some integer again. So again, we can just solve for beta here. We get beta is equal to, there now we have 2m plus 1 pi. And so this, I guess I should really put a little approximation thing. So this will be close enough. So this is close enough for a intensity maximum. So in your book, they show you how close this approximation is to the actual numerical solutions. So you plug in various values of m, and it's pretty close. So this is good enough. And then if you want to take this formula and basically for beta and basically plug it back in here, you'll get an approximation of your intensity maxima. So you'll just take that beta is approximately equal to, we said 2m plus 1 pi. Plug that back into your intensity equation, and you'll get that the intensity maxima are approximately at this location. Oops. So this is good enough for us. Okay, so these are our location of the intensity maxima. Again, you can just sort of take these formulas as a given. I would make sure that you understand like this part at least for all these problems which we've done, in previous chapters, when we solve for like sine of something is equal to, plus or minus 1 or 0. That kind of stuff is important and obviously pops up a lot in physics. But obviously you don't need to worry about transcendental equations right now or anything like that. So as long as you understand how the approximation works, that's totally fine. Okay, so now looking just sort of qualitatively at the widths of these maxima. So the width or the angular spread of the central maximum, so that's where m is equal to 1 here. So when we have m is equal to 1 and we have a small angle, so this is at a small angle, and m is equal to 1, we know we have a sine theta is equal to m lambda, right? But we said it's a small angle, so that means we can approximate sine theta as theta. So we can have a theta. And now we said that we're looking at the central maximum. So as you can see here, the central maximum is going to be bounded by the first minima, right? It's going to be bounded by the m equals 1 and m equals -1 minima on either side, the dark spots, I should say. So we can talk about the width of the central maximum by talking about where this m equals 1 and m equals -1 dark fringes occur, how their angular spread basically. So we're looking at m is equal to 1 here, so that just gives us lambda. So we can just rewrite this. We can write theta as lambda over a. So that gives us our angular spread for that central maximum. And now you can see here, if we have that a is equal to lambda, so if the size of your slit is equal to the wavelength of that light, you're going to get like a huge central maximum here. So we want the wavelength to typically be smaller than the slit, so we want lambda to be less than a. So you can see here when a is about 5 times as big as the wavelength, you get about 20 degrees here. And then when a is equal to 8 times the wavelength, you get a much narrower central maximum. So that's just how the width of that central maximum is related to the slit width and wavelength of our light. Okay, so moving on, let's do an example with the intensity. So here we have the intensity at the center of a single slit diffraction pattern is I0. What is the intensity at a point in the pattern where there is a 66 radian phase difference between wavelets from the two edges of the slit? So that's going to be beta, remember. Okay, so let's do that part first. So the phase difference between the ray coming from the top of the slit and the ray coming from the bottom of the slit, as we said before, let me just get the picture back here. We said that is equal to beta. So they're saying beta is equal to 66 radians. Did I say degrees or radians? 66 radian phase difference. So that already is going to be really big because we know there's only 2 pi radians in a circle. So we're looking at 66 radians. So we can already guess that we're going to be at like m equals 10 or something, because a 66 radian phase difference is like pretty big. So, okay, we know that beta is equal to 66 radians. And we want to know what is the intensity at that point. So I is equal to what? Okay, we just have some initial intensity I0. So we can just plug that right into our formula. We have sine of beta over 2 squared. Okay, so let's just plug this in. So we're going to have sine of 66 over 2 is 33. So we're going to have sine of 33 radians. So be really careful that you plug in radians, not degrees here. Radians divided by 33 radians squared. So you plug that into your calculator and we get 9.2, so this comes out to 9.2 times 10 to the -4 I0. So, as we said before, the intensity drops off very fast. So this intensity is like basically 0. You wouldn't really be able to see this intensity. So this intensity has dropped off quite significantly. Now, let's look at part B. So if this point is 7 degrees away from the central maximum, how many wavelengths wide is the slit? So let's first just write down our formula for beta, just to have, so this is A and this is B. So beta, we said, is 2 pi over lambda times A sine theta. So they're telling us this point is 7 degrees away from the central maximum. So that means that this here is 7 degrees. So this theta is 7 degrees. Okay. And they want to know now, so we know beta, we know theta, 2 pi is always 2 pi, and we don't know A here, and we don't know lambda, but they want to know how many wavelengths wide is the slit. Now, if we had the the width of the slit, let's say the slit was 10 meters wide, and the wavelength was 2 meters, we would just divide the slit width by the wavelength, right? To get how many wavelengths fit in the slit, and we get 5 in this case. So all we have to do, all we did here was just divide the slit width by the wavelength, and that gave us how many wavelengths were in the slit width, in the slit, right? So now we see that we have that exact ratio in this equation, right? We have A over lambda. So actually all we have to do, since we just want to know how many wavelengths are in the slit, all we have to do is just solve for this ratio A over lambda. So let's just do this. So we're going to solve for A over lambda. So that's going to give us A over lambda will be beta over 2 pi sine theta. Okay, and so then let's just plug things in here. So beta we know is 66 radians, 2 pi, and then sine of 7 degrees. Now here, it is okay to keep, as I said before, it is okay to keep this 7 in degrees because you're just evaluating sine of 7 degrees. So whether you change 7 to radians or not, the sine of that is going to be the same. Whether you do sine of 7 degrees or sine of 7 degrees in radians is going to give you the same sign. So evaluate this however you want, and then you will get here, this comes out to 86. So you end up with, there's 86 wavelengths in this slit, and we didn't have to find the wavelength, we didn't have to find the width of the slit, we just had that ratio there and we were able to solve for it. And now if you wanted to with this problem, you could also figure out approximately what intensity maximum or minimum we're at. If you take beta is equal to 66 radians, and we said that beta is a maximum around here, and then we also know where it's a minimum. What you can do is figure out what 66 radians is in terms of pi. So 66 radians is about equal to 21 pi radians. So I just rewrote 66 in terms of pi. So it's about equal to 21 pi. And now that is approximately 2 times 10 plus 1 pi, right? I can rewrite 21 as 2 times 10 plus 1. And we know that this is the form of our approximate maxima that we found before, right here, right? 2 times 10 plus 1 is 21 times pi, will give us about 66 radians for beta. So now we can see that this is about like the 10th intensity maximum that we're looking at, which, as I said before, is really far out, and that's why our intensity was essentially 0 here, because we don't usually see anything past m is equal to 3. So we can see that, as I guessed in the beginning, that we were going to be looking at something way past m is equal to 3, like m is equal to 10, because 66 radians is pretty big. Okay, so let's do one more example. So that was a little bit tricky. So let's do one more example. So in the experiment described in example 3.61, so that was, we did that on Tuesday, and this was the diagram. We had a slit here. The distance between the m equals 1 minima, the dark spots here, were 32 millimeters, and the screen was 6 meters away. Okay, so we want to know, in this setup, the intensity at the center of the pattern is I naught. What is the intensity at a point on the screen 3 millimeters from the center of the pattern? Okay, so for this problem, there are a couple things we just need from when we solved the first examples, when we did example 36.1 on Tuesday. we had also that the wavelength of light was 633 times 10 to the negative 9, so it's nanometers. And then we also found in that problem that the slit width was 2.4 times 10 to the negative 4 meters. So we just need those two other things to finish solving this problem. So now we want to find the intensity. So obviously we're going to be using this formula again. So you can kind of guess that we're going to want to find beta first. So we obviously need beta if we want to find the intensity. So let's find beta. So beta we know is 2 pi over lambda a sine theta. Now we have lambda, we have a, but we don't have sine theta, right? So we need to find what theta is. Now we're looking at a point that we said is 3 millimeters from the center of the pattern. So the center of the pattern is right here. And we know that the dark spots aren't until 32 millimeters out. So we can guess that this 3 millimeters is going to be basically like right in here. It's essentially going to be at the maximum, but just a little bit off. So we should be expecting an intensity that's very close to 1, right? Because it's in this central band here. So what we can do is this is where the light is coming through right here. This is the screen over here. Let's say this is our 3 millimeters. We have 6 meters here. We can find theta because theta is going to be like that. And we know that theta is going to be very small, obviously, right? Because we have 3 millimeters on one side, 6 meters on the other side. So we can use a small angle approximation of tan theta being approximately equal to theta. So we can just say that theta is going to be opposite over adjacent here. So theta, we're going to say is opposite over adjacent, which is just 3 millimeters divided by 6 meters. So we've got, this is the opposite side, adjacent side. That will give us essentially theta. So we just do 3 times 10 to the negative 3 because it was in millimeters divided by 6. And this gives us, for theta, we get about 5 times 10 to the negative 4. So that's our theta now. And now, since also our small angle approximation, we know that sine theta is approximately equal to theta, which is approximately equal to tan theta. So it's okay to, kind of mush around your sine and your tan when you're at these very small angles. So, okay, so now we have theta. So now we can just, now we basically just have to plug things in. So now we have theta here, we have a, we have lambda, and then we just have to plug it into this formula and we'll get I naught. So let's plug that in. So we have now, or let's find beta first. So let's find beta. So we have 2, actually let's make it a little bit easier. And since we're gonna have to plug in beta over 2, let's just solve for beta over 2. So beta over 2 will be equal to pi times a over lambda sine theta, right? Because if we're doing beta over 2, this 2 will cancel out here. So this is equal to pi times a, we said was 2.4 times 10 to the negative 4. Sine theta, we said is approximately just theta, which we found here. And then this is all divided by the wavelength. Let me add another page in there. Okay, so we have all this. So plug all that into your calculator here. And then we will get, so this comes out to beta over 2 comes out to 0.6. So now we have beta over 2 and we can plug that back into our intensity equation. So we get sine of 0.6 radians divided by 0.6 squared. And this comes out to 0.89 I naught. So this is what we expected basically. We expected the intensity 3 millimeters away to be very close to the maximum intensity of just I naught. And here we have, it's basically 90%. So that makes sense. That is what we expected. So, okay, so I know these intensity problems can be a little bit confusing, but yeah, just work through the examples that we do. Okay, so let's move on. So this might look a little bit worse now. So this basically, when we did, or when you guys did in chapter 35, the case of two slits, you assumed that they were essentially infinitely small. And then what that did was, do I have a picture? Yeah. So what that did basically was it assumed that the intensity of every maximum was the same. And now obviously that's not really going to happen in real life. They're going to fall off, as we just saw, or as you can see when you actually do these like diffraction and interference problems. If you're doing them in lab, you would see that they fall off. So obviously they're not going to be like infinitely bright all the way out to like m is equal to infinity. They're going to fall off to 0. So what happens is, now when you have a single slit diffraction where you have like a finite width of your slit, right? You get this pattern, which we've already seen. And then when you combine that with now like the physical case of two slits with finite width, this function creates an envelope around this function, and this function is like pressed down so that it fits in this one, and you get what looks like this. So you can see you kind of have both functions on top of each other. So this is the intensity trailing off as you go to higher and higher m's, but within it is the intensity pattern that you found in chapter 35 here. So if you want to write this as an equation, obviously, you have this cosine squared function, where this was from chapter 35, where this is the separation between the slits. D is the separation between the slits here, and phi is given by this, which you did in chapter 35. So you have this cosine phi here, which corresponds to this pattern. Then you sort of like, when we multiply it by the intensity pattern that we just found with this sine of beta and everything, where beta is given by this, it will create this function here where it trails off. Okay, so we're not going to do any examples with this, and I'm not going to ask you, you might have a question on the homework, but on the exam, I won't ask you a question with this formula. The intensity with just the beta one is definitely fair game, but this one we're not really going to go into that much. So, if you have a homework problem to do, that's as far as we're going to go with this whole formula here. Okay, so that's, and then, and one other thing. So what can also happen here is you can see here that it kind of looks like we should have a maximum right here, right? If we kind of traced out this little, these little maxima here, it looks like there probably should be one here, but this bigger function goes to 0. So you can have where this function sort of cancels out a maxima that you would have if you were just looking at this function. And that happens when D is a multiple of A. Now you can go ahead and like prove that to yourself, but like I said, we're not going to go too deep into this part. So it's important just to know that that can happen where they can basically cancel out each other's maximas, basically. Okay, and then one other thing, again, we're not going to go too deeply into this, so this, just kind of knowing what these plots look like is sufficient. If we have multiple slits, so we're not at our diffraction grading yet where we have like thousands of slits per centimeter, but let's say you have, here we're looking at 2 slits, 8 slits, 16 slits. When you start adding these slits, you get tiny little maxima in between your principal maxima. And what will happen is you'll get n minus 1 minima in between those principal maxima here. So this is the case of 2 slits, so n is equal to 2, so you have 2 slits. Now 2 minus 1 is obviously 1, so you have 1 minima in between each maxima, right? So you have a maxima here, a maximum here. You have 1 minima in between them. Now, if we go on to the case of 8 slits, so if we have n is equal to 8, we get 7 little minima and 6 little maxima, but 7 little minima in between these 2 big maxima here. So if you count these, you have 1, 2, 3, 4, 5, 6, 7 mini minima in between your principal maxima here. And you do that, that's on each one. And then the same thing if you do n is equal to 16. If you have 16 slits, you'll have 15 little maxima. So So if you do the same thing with 16, n is equal to 16, you'll have 15 little minima in between these two principal maxima, and you'll have that at each point. Okay, so again, we're not going to go too deeply into this. This is sufficient for now. So one of the main uses of these diffraction gratings is it's very commonly used in astronomy. Also, it's used to basically identify atoms. So when you have gases and atoms interacting in the sun, as they move through the atmosphere of the sun, because the sun has an atmosphere, as it moves through like all the gases in the atmosphere of the sun, we can determine what those elements are by passing the light basically through a diffraction grating. And what we'll see is that there are certain spots on when the light diffracts, and we get this like little rainbow, which we did a little bit on Tuesday. You see these like black bands here. Now you can measure where those black bands are, right? Because you can say, this black band appears at 0.5 degrees and this one is at 1.2 degrees. So you can figure out where these black little bands are of missing light. And what that's caused by is atoms in the sun, certain atoms absorb light of a certain wavelength, a certain frequency. So that means that the light of this corresponding wavelength is getting absorbed by something in the sun. And you can also do the same thing. You'll see emission spectra where certain atoms only emit light of certain wavelengths, and it will be just like this, but opposite, where you have all black and then you just have a couple of bright spots corresponding to different atoms. So all different atoms have these different spectra where they only absorb and emit light of certain wavelengths, and this is used quite extensively in astronomy to identify what the atmosphere of exoplanets and what makes up stars. This is used very extensively to identify what the elements in that atmosphere are. So this is one use of these diffraction gratings. Okay, so now we're going to get into another very important use of diffraction is with X-ray diffraction. So X-ray diffraction is super interesting. It gets like very complicated very quickly. So you have like these crystals, and crystals have a very regular shape. Now, I know a lot of people, well, crystals used to be a big thing on the physics GRE, but now they're taking away the physics GRE. So I don't know if people study crystals as much as they used to. But crystals used to be a very big thing on the physics GRE and like knowing how they were shaped and stuff. But they have very regular spacing. So like you'll have layers of the crystal, and these layers are about every 10 to the negative 10 meters. So that's the spacing between layers in your crystal. I think I have a picture. Yeah, I have a picture here. So you have these crystals that are spaced very regularly, and the spacing between layers is about 10 to the negative 10 meters. Now, this is about the same wavelength as an X-ray. So what this means is that crystals basically create like a natural diffraction grating for X-rays. So what you do is you take an X-ray, you shine it basically through a crystal, and it creates these like really cool patterns. It gets diffracted through the crystal, and it creates these really cool patterns. And you can basically reconstruct the structure of these crystals. And basically then what you do is you can actually do like a Fourier analysis and reconstruct the shape of the crystal from just getting this diffraction pattern. And we'll see one of the uses of this in a second. But so basically what happens is, so we have here, this is table salt, sodium chloride. So you have the atoms are spaced very regularly, and you have basically like this array of atoms. And then as we said before, they're spaced at very regular intervals. So if you shine a X-ray on the surface of one of these crystals, you'll have the light ray coming in like this, and it will get scattered as it hits the crystal. So what we can do is you can look at the light scattered from adjacent rows in your crystal, and what you'll find is that it's constructive when the path length, the difference, is 2d sine theta. and we want that to be an integer number of wavelengths. So we're going to end up with an equation like we had for all of our other cases. And what we're going to have basically is, this is called the Bragg condition when we are talking about interference in a crystal, X-ray diffraction in a crystal. So now we have, again, constructive interference. So this is talking about a bright spot because we're looking at constructive interference now. So we have the condition for a bright spot is 2D, where D is the spacing between adjacent rows of your crystal. Sine theta now is the angle from the surface to the bright spot. And then M is the number of the bright spot, and lambda is the wavelength again. Now, one thing to be careful of here is that we've spent a lot of time where we have like the angle of incidence is measured from the normal, but in this, unfortunately, it's actually measured from the surface. So it's like backwards from what I've already been drilling into your head with all of our other angles. So that's a little bit confusing. So be very careful of that. This is our angle theta. So this is the surface of the crystal. This is the light ray coming in like this. And now theta is actually measured from the surface, not from the normal like we've been seeing. We did like, optics and stuff. So be really careful of that. I know it's really confusing because everything was kind of developed at, different times and independently of each other. So optics was developed one way, and then, this guy, Sir Bragg, did it another way. So it's a little bit confusing, but unfortunately that's what we're stuck with. So this theta here is the angle from the surface to your bright spot. Okay, so let's do an example with this that might help a bit. So here we have a beam of 0.154 nanometer X-rays. So that's going to be the wavelength is 1.54 times 10 to the negative 9 meters. So we direct this beam at the plane, so at certain planes of a silicon crystal. As you increase the angle of incidence of the beam from 0, the first strong interference maximum occurs when the beam makes an angle of 34.5 degrees with the plane. So what that means is that we have our crystal here, and we have our light. We start at 0 degrees, and we keep increasing this angle of incidence at our crystal here. So we're increasing this theta. When we get to theta is equal to 34.5 degrees, that's when we see our first bright spot, our first interference maximum. So we want to know how far apart are the planes. So here we can just plug in our, do our Bragg condition. So we're going to have 2D sine theta is equal to m lambda, and we're looking at a maximum. So we have, we're looking for D here. So D will be m lambda over 2 sine theta. So m we said is 1 because we're seeing our first interference maximum. So that's going to be 1 times 1.54 times 10 to the negative 9 meters divided by 2 times sine of 34.5 degrees. Okay, so just plug that into your calculator, and this comes out to 0.136 nanometers. And this makes sense because, as we said before, we want the spacing of our crystal to be about equal to the wavelength. They want to be on the same order of magnitude. So here we have, they're basically the same order of magnitude. Okay, so we found the spacing. That part was relatively straightforward. Now we want to know, will you find other interference maxima from these planes at larger angles of incidence? So what that means is if we keep increasing this angle, will there be other interference maxima? Will there be other bright spots? So we're going to be looking for theta. So let's get sine theta by itself here. So we've got sine theta is equal to m lambda over 2d. And now we know that lambda and d aren't changing, and 2 obviously doesn't change either, right? So what we can do is let's rewrite theta is sine inverse of m lambda over 2d. So let's plug in what we have here. We have m lambda, we said, was 0.154 times 10 to the negative 9, and then 2 times 0.136 times 10 to the negative 9 for d. So this gives us m times 0.566. So that is 566. Okay, so this is sine is equal to this. Now, if I wanted to find theta, so we can change m here, right? So we can see, okay, are there other maximas? Let's change m. We can have m as 1, m as 2, m as 3. So if you do m is equal to 1 and then do sine, solve for theta, do sine inverse of 1 times 0.566, that will give you 34.5. So if we do sine inverse of 0.566, which means that m is equal to 1, you just get back the original angle, which we already found. Well, now let's try m is equal to 2 and see if that works. But we can already see that m equals 2 is not going to work, because if we try m is equal to 2, now we're going to get a number that's bigger than 1, right? We're going to have sine of theta is equal to like 1.1 or something like that. And we can't do sine inverse of a number bigger than 1, obviously. So that means that we don't have any maxima beyond m is equal to 1, and we're not going to find any like new angles that give us a interference maximum here. It's just going to be this one at m is equal to, it's just going to be that one at 34.5. Okay, so then this X-ray diffraction stuff was actually used to discover the double helix structure of DNA. So it's like a really interesting story because there's some crazy stories about like Watson and Crick not exactly being the nicest people. So there's some interesting stories surrounding them. And actually they got their idea for the double helix from this woman, Rosalind Franklin. And she was basically known as being able to get these really clear pictures like this from the X-ray diffraction. And they were looking at DNA. They didn't yet know what structure it was. So she got this really nice picture. This is actually the picture where they used X-ray diffraction to take a picture of DNA. And it was actually this picture that gave Watson and Crick their idea for the double helix structure. So there's a little bit of a scandal with this whole story, because some people feel like they unethically took her work, because she had taken this really clear picture of this DNA, and one of her coworkers apparently let them into her office to see this picture without her permission. And this is what ended up inspiring them to come up with the double helix structure. So anyway, so that's how we ended up discovering that DNA has a double helix structure. It was actually this picture that Rosalind Franklin took. And she ended up dying super young because she was working with X-rays and all kinds of radiation stuff. So she ended up dying of cancer at 35 or something. Okay, so that's a little bit of history with our X-ray diffraction. So now let's move on to some applications again. So we've been looking at slits, but any opening, so an aperture just means an opening. Any opening of any shape will cause a diffraction pattern. So typically optical instruments will be using a circle, like a camera uses, a circle, a telescope uses a circle. So we're usually going to be looking at circles in this case. And as I mentioned on Tuesday, if you hold a sphere in front of light, you'll get actually this bright spot behind the sphere. And this was part of what sort of convinced people that light is actually a wave, is because this can't happen with if you look at light as particles. So you can get this bright spot if you hold a sphere in front of light, but you'll also obviously get this same well, I don't know if it's obvious, but you'll get this same pattern if you shine light through a very small hole. So if we have a very, very small hole here and we shine light through it, we'll get a central bright spot from where the light just shines directly through, which you would expect, but then we still get this diffraction pattern around the edges. So then we get kind of concentric bright and dark spots around this central maximum again. And so this is important in, as I said, like optical instruments like telescopes and stuff, because if your telescope is not powerful enough, objects that are very close together will just look like they're the same object, and you won't be able to resolve them. So this is what it looks like here, and we're going to talk about this in a second. If you have two objects that are very close together, and you have a very small opening, very small aperture here, it's going to look like the objects are almost right on top of each other. And then as you get a slightly bigger aperture, a slightly bigger opening here, then you can see that the diffraction lessens a little bit, and you can see that these are actually two separate objects. So this is important, obviously, in astronomy. You don't want the diffraction pattern of like one star to overlap with the diffraction pattern of another and then not be able to tell that they're two different stars or two different galaxies. So this is very important, as I said, in telescopes. So the first thing we need to do is we can write an equation for basically the angular like spread of this central maximum here. So that's the first thing we need. So the angular radius of the first dark ring, which would also be the angular radius of that central maximum, right? Because the central maximum is bounded by the dark ring. So the angular radius of the first dark ring is given by this. So sine of theta, where that's the angular spread, that theta, is 1.22 times the wavelength over the diameter of the opening, the aperture. So this gives us, as I said, the angular spread, or it tells us where that first dark ring is right here. So that this first dark ring is given by that previous equation, the angular theta 1 right here. So you go from the center to the first dark ring, that is theta 1. And then this center maximum also is called the Airy disk. So Airy has also some functions named after him. If you take quantum mechanics, you'll use Airy functions. So this center disk here is called the Airy disk. And then we can use this equation in what is called Raleigh's criterion. So Raleigh's criterion just states that objects are just barely resolved. So they're just resolved by an optical instrument if the center of one diffraction pattern coincides with the first minimum of the other. And so the minimum separation of two objects, so if you look at two stars in the night sky, you can measure their angular separation. So this minimum separation that can be resolved by an optical instrument is called the limit of resolution, or sometimes you'll see that referred to as its resolving power. So here's just a picture of kind of how you can see the intensities. So here you can't discern that there are two distinct objects here because their central maximas completely essentially coincide. So this is sort of what the intensity pattern looks like. Then as you start increasing your resolving power, you can start to see that there are two objects. And then once you have, as I said before, the center of one diffraction pattern coincides with the first minimum of the other, then you can see that they're two separate objects. So this is called Raleigh's criterion. And we're going to do an example with this in a second. There's just one other thing that I just want to quickly go back to with cameras. If you're doing, when you do problems with Raleigh's criterion, you'll probably see, especially if it involves a camera, you'll see something called the F number. Now, I'm not going to test you on F number, so if you don't care, just move on to the next slide. But if you are doing problems and you see F number, all F number is just the focal length of the lens divided by the diameter of your opening of the aperture. So that's all F number is. I think in your book, a lot of the problems with Rayleigh criterion used this F number thing, and since we didn't really go into it, I just wanted to just quickly remind you of that. But as I said, I'm not going to test you. None of the Rayleigh criterion problems that we do on the exam will involve F number, but in case you come across it, that's what it is. Okay, so now let's do an example with Raleigh's criterion. So here we have, this is a pointillism painting. So I don't know if you've seen in like your art or history class or something. Pointillism was this style of painting where instead of like painting with brush strokes, they would just do like little dots basically to make the entire picture. So you can see here, if you look really close, you can see this isn't actually just like a crappy, pixelated image. All of the image here is actually just really little dots that then come together to make an image. So pointillism basically like kind of plays on the resolving power of your eye because it has all these little dots that when you're far away, you can't see that they're individual dots. You just see it as like one flowing picture. So what we want to do here is we're going to assume the separation between centers of the colored dots. So each little dot here on a painting is 2 millimeters. So we're going to call that, let's call that small d is equal to 2 times 10 to the negative 3 meters. So each little dot is separated, the center of each dot is separated from the center of another dot next to it by 2 millimeters. And the diameter of your pupil is 1.5 millimeters. So that's D, that's the diameter of the aperture is our pupil, is 1.5 times 10 to the negative 3 meters here. So what is the shortest viewing distance from which you cannot distinguish any individual dots? So obviously, as you're very close to the painting, you can see that they're all individual dots. And then as you back up, eventually it's going to blur into a picture. So it's saying what's the shortest distance from which you can no longer see the individual dots. So what we're going to do here is let's say we have a dot here and a dot here. And this, our eye is over here, and this is the distance D, right? So what we want to know for Raleigh's criterion, we want to know what this angle theta is. So we first want to find this. So remember we have sine theta is equal to 1.22 lambda over D. So the first thing we're going to want to do if we want to find the length that the distance we have to be back, we want to find this theta first. So we're going to be using a small angle approximation because this side of the triangle is going to be much, much smaller than this side. So we're going to be able to use a small angle approximation. So what we can do is say, okay, theta is about equal to opposite over adjacent because we're using a small angle approximation, which here the opposite over adjacent is d over 2, right? Because opposite here is 1/2 of the distance d. So it's going to be d over 2 divided by this length L. Now this length L here is what we're looking for because that is the distance that we're standing away from the painting. So this is the L that we're actually looking for. So we don't need to actually explicitly solve for theta now because we can just use this small angle approximation and just solve for L directly now. So now what we can do, so now remember we want the first minimum of this diffraction pattern, let's say from this dot, to coincide with the center of this one. So that means when we plug in theta here, remember theta is the angular radius from the center to your first dark spot, your first minimum. This theta here is actually this entire angle, right? Because we're going from the center here and then to the first dark spot, which we want to be right over this second dot. So we're actually looking at 2 times theta. So this theta 1 will be just d over L because we're looking for this entire theta here when we plug it into the Rayleigh criterion. So we have theta 1 is d over L. So now let's just rewrite this. So we have, I'll just rewrite the Rayleigh criterion. So we have 1.22 lambda over d. So we said that theta 1 was equal to d over L, and L is what we're looking for. That's the length, how far we are away. So let's just do d over L. We'll replace sine with d over L, since again we're at the small angle approximation. Theta is approximately equal to sine. So we have d over L is 1.22 lambda over the diameter of our pupil. And then let's just solve for L now. So all we have to do is solve for L, and we'll get, let's see, we'll have d over 1.22 lambda times capital D. Okay, so let's plug things in here. So we had little d, we said was 2 times 10 to the negative 3. The diameter of our pupil we said was 1.5 times 10 to the negative 3. Then we have 1.22, and then we have to plug in lambda if we want to find an actual value for L. So what we can see here actually is that the value for L is going to depend obviously on what we plug in for lambda. So that means that different wavelengths of light, different colors of light, will actually be able to resolve differently. So what you'll see here is that the longer or the bigger lambda is, then the shorter L will be. So we'll actually be able to distinguish like blue light for a longer distance than would be able to distinguish red light. So red light will become indistinguishable first because it has the longest wavelength, and blue and violet will be distinguishable the farthest because it has the shortest wavelength. So let's just plug in like 400 nanometers just to get an idea for what L is. So we'll do 400 times 10 to the negative 9. So plug that into your calculator. This comes out to about 6.1 meters if we use 400, but like I said, I just used a random wavelength of light. If it specified like a color, then you would use that corresponding wavelength color. So here, okay, so about 6 meters. So if you wanted to plug in here like red light and you wanted to plug in let's say, if you wanted to plug in red, you'd plug in maybe like 700. Here you'd plug in 700 times 10 to the negative 9. You would get instead about 3 meters. So you can see that red actually becomes indistinguishable. The red dots become indistinguishable at 3 meters, whereas some of the more bluish dots are not until 6 meters. So, okay. So this is how the Rayleigh criterion works and the resolving power. So that is it for today. That's it for the whole class. So we're done with our material. So like I said, I will try to get up a review for the final, if not Friday, I'll definitely by Saturday night. So I'll try to get one up as soon as I can. But okay, so yeah, so that's all the material we're going to cover. I hope even though things were a little bit crazy this quarter, I hope you managed to learn some physics anyway, with things not being ideal. So yeah, so good luck on the final, and I will see you guys for our final review.